changing back to the because like she said, there was a community wrong with it. You know, comes into my meeting and says, yeah, there was a student, their study plan was like,
All right.
So I was like, I know that.
All right. So we have been talking about the normal distribution and how we find the probability of being above, below, between certain values. So we'll talk about two other types of continuous random variables we have, and then we'll kind of return a little bit to normal distribution because we'll have to start talking about things like sample. So if we had, instead of a normally distributed variable, an exponentially distributed variable, I guess, it would look something similar to this, right? So the shape of the distribution kind of looks something like this. So what this is really telling us is that the probability of seeing low values is relatively high, while the probability of seeing values further out starts to get smaller and smaller. Now, with the exponential, we can kind of think about it as whatever we see. So we've got this random variable x, and we can find kind of the mean of x by looking at some data, right? So I've got this variable in a data set. I calculate the average, or I calculate the mean. The mean is actually going to be 1 over whatever this lambda is, and lambda is kind of a parameter that's going to be specific to the probability density function. Okay? So if I can calculate the mean from that variable, I can back out what lambda is, right? So let's like in the actual variable I'm looking at in Excel equals average of the column, and I get an average of 50. Okay? Well, what that tells me is, right, that basically, right, if I rearrange this, lambda would be 1 over 50. Right? So I just multiply both sides by lambda, divide both sides by 50. So here, the mean is equal to 1 over lambda, or if it's easier to think about, lambda is equal to 1 over whatever mean that you're seeing from the data, from the actual variable. So once I have lambda, I can then start to find the probability of being above or below certain values. Right? So maybe I want to know what's the probability that x is greater than or equal to, actually I'll do less than or equal to 55. Well, if I'm looking at my probability density function, right, I've got lambda now. It'd be as easy as 1 minus what? E to the negative 1 over 50 times x, right? Lambda times x, so 1 over 50 times 55. Right, so it's really a similar process, I guess. We're using a slightly different probability density function, right? We don't have to look it up in a table because this equation is a little bit easier to deal with. I guess kind of the added part of these problems a little bit tougher is I can observe this mean, and using that mean, I then can calculate lambda. That's kind of like the added step that we really haven't had to do something like that yet. So we'll put some actual values to this and work through a little problem here. But does this kind of just make sense? Any questions on this before? So let's say we're looking at like a car battery, and we know that it's going to last a certain number of days before it decreases. You know, so when will this kind of battery life kind of give out? Well, on average, this battery has a life of 2,000 days. Okay? So that's the value we see from the data. That's our mean.
Dialogue days are great. There's only so much board space.
So we've got kind of our mean, right? Our mean is 2,000. So if I rearrange this, my lambda is going to be 1 over 2,000, right? Or what, 0.00005? Or 4 zeros, am I looking at that right? There we go. No, add a 0. 0.0005. So I've got my lambda. At this point, it's just a matter of using got probability density function, plugging in that lambda, and finding the probability that I see this battery last longer or less than a certain amount of days. Right? So I've got my lambda. What's the probability it lasts more than 10 years? Okay. Well, 10 years, if I had this average life in days, what, 10 times 365, so 3,650. No, yeah, 10 years. I did have 10 years. Okay. So this is my value X I'm interested in. I have lambda. So it's 1 minus e to the negative lambda. So 1 over 2,000 multiplied by the X value I'm interested in is 3650. Oh, I actually asked for what's the probability? It's more than 10 years, right? So notice this gives me the probability that it would be less than 10 years. So I can still use this to find the probability it's greater than 10 years by doing what? Just taking this probability and subtracting it from 1. Now notice if I subtract this from 1, 1 minus 1 is cancels, the negative sign is here, and so that I'm actually just left with, and I had a negative sign here, there is, yeah, there's a negative sign, okay. So am I remember that correctly? And then I'm just left with that kind of E component there. Right? So anytime I want to do the probability is greater than a certain value, I can do 1 minus that, but I can also remember, well, yeah, 1 minus this equation is just going to be this but positive. So plug all our values in, we could actually find the probability it's less than. We could then take that probability and subtract it from, right? Subtract it from 1, right? Or just use that E component to get that probability. Right? 2 different ways of doing the same thing. I can find the probability it's less than 10 years, and then whatever this probability is, subtract it from 1. Or I can remember, well, if I take this and subtract 1, I'll just be left with a kind of natural number E component. And then I don't have to do any work after that. Questions there? Yeah.
So when you do, like, instead of doing the 1 minus, you just get rid of the negative and that.
Yeah, so here, I'll write this out. I'll write it out, not with numbers, but just the formula. So let's say I want the probability X is greater than or equal to a certain value. That's exponentially distributed. So I know that's 1 minus the probability that it's less than this value, which is 1 minus e to the negative lambda times X. Well, 1 minus 1 cancels. When I'm subtracting this here, that becomes a positive. So if I want the probability of being above a certain value, it's just going to be that E component. Does that make more sense?
Yeah.
Okay. I had a little bit too much going on here, I think, with the numbers and stuff before. So. Okay. So I don't think these ones are too bad. The next one we're going to do is terrible. I mean, I shouldn't say it's terrible, but it's not near as simple. Okay. So, but the problem is this one's more common. This is a more frequent distribution that we'll see. So we have to know how to do it. So I've got something that's log normally distributed. It's going to look close to a normal distribution depending on the variance. But notice, like, it's kind of like it's almost normally distributed, but with this like real long, kind of like a thicker right tail. So the mean of whatever this, so let's assume we have this variable X, right? And we know that X is normally distributed. So we're going to take this log normal distribution and convert it into a normally distributed variable. So the way that we're going to do that is whatever we see in the data, right? We see the mean of this log normally distributed variable. So we can use that mean and use the variance we can calculate with the data to come up with what the mean and the variance, or sorry, mean and standard deviation should be for this underlying normally distributed variable. We can call that y. So I think here I have like an example, and I'll go back to those equations here in just a second. So I think I have an example here. We kind of see this play out. All right, these look like normal distributions, but kind of have this long, thicker right tail. So we'll go through an example, and then I'll go back to the equations, and we'll kind of start plugging them in. But I want to kind of give a little bit more of an insight as to what's going on. I keep forgetting where I put my erasers. So what we see is this variable y. That's what we see in the data. We can graph it out and see this variable is log normally distributed. And the reason why we say it's log normally distributed is because there is some variable we can't see x, where we know that x is normally distributed. Right? And y is just a function of that variable, but e to the power of that variable. Said differently, I don't know where everyone's at with mathematics, but in order to kind of get rid of this e, if I take the natural log of both of these, x pulls out front, the natural log of e is 1. So I actually can also think about that equation that I started with up there. I can rearrange it to be equal to that. And this makes a little more sense now, because now the variable that I see in the data, y, well, it's equal to a normally distributed variable, but only if I take the natural log of it. So that's why we say it's log normally distributed, right? If I take the natural log of this variable, I know that it's going to be normally distributed, okay? So what we see in the data is the mean and the standard deviation of the variance of this y variable. But we know that the natural log of y is what is normally distributed. So we can think about different values for y. And what we're going to do is we're going to say, okay, what's the probability that y is less than 500? Well, the only way we can find that probably that y is less than 500 is say, okay, what's the probability that the natural log of 500 is less, or sorry, that x is less than or equal to the natural log of 500. So we're going to have to be looking at the natural log of these different cutoff values that we're interested in. Now the problem is, once I have this as a natural log value, well, this is my x value, whatever number this ends up being, that's my x value, but I would still need so you can almost think about it here, my x value that we had x before, it's just gonna be whatever that natural log is of the cutoff you're interested in. The problem is we need to subtract the mean and the standard deviation of this normally distributed variable x. So how do we find that mean and standard deviation? That was using these equations, right? So if it makes a little more sense here, you're finding the expected value or the mean of x and the standard deviation of that normally distributed variable x. So the means and the variances you're using here, if you want to, you could write y in there, right? Because those are going to be the mean and the variance that you observe looking at that variable y, that's the one you actually see in the data. Okay. So yeah, it makes it easier to think about variance and mean of that y variable that you're observing, and then that underlying normally distributed variable x, that's what you're calculating the mean and the standard deviation of. Any questions on that? I'm surprised that it's not. Okay, let's work through a problem, maybe make it a little bit more sense here. So we see this variable y in the data, and it has a mean of 500 and a variance of 5. Okay. So what we're going to do is come up with what the mean or the expected value is for this x variable. So we're going to take that mean of 500 and variance of 5 for the y variable, plug it into our equation that gives us the expected value of x. Or you can kind of think about it here, it's giving me the mean of x. So I have what, 6.21. And then we use that same mean and variance, and we just plug it into that equation we had for the variance of x, which is 0.0, once we plug those in, 0.00002, so 0.00002 here. Well, now I've got the mean and the variance of this normally distributed variable, and I can start to find the probability I'm above or below certain values. Okay. So really it's just a matter of, once you have that mean and variance, plug them into those equations to get your new mean and your new variance to this underlying normally distributed variable x. This is like duration of your phone. I can't remember. I think this must be in days. Oops. So we've got this underlying normally distributed variable. So from here, it's a little bit tricky. But now let's say I want the probability that, so if this is like the number of, I don't know why this doesn't make sense with the numbers that I gave, but just bear with me. So let's think about the duration on my phone. Maybe this is like 500, well, that might make sense, 500 minutes or something, right? So what's the probability that the next time I have my phone that it lasts for less than 400 minutes, right? So I'm thinking about, I want to know what's the probability y is less than or equal to 400. Well, I know that the natural log of y is this normally distributed variable x with a mean of 6.21. Was there 3 or 4 zeros? 4. And the variance of 0.00002. So if I want to find the probability y is less than or equal to 400, what it actually would need to do is convert that value of 400, right, into a z-score. The problem is this mean and variance are for the natural log of y. So when I'm thinking about kind of like my x value here, so I'll subtract the mean of 6.21. I'll divide by the square root of that variance, right? Square root of 0.00002. But then here, I won't put in the value of 400. I mean, first of all, if I put 400 in here, what's going to happen to my z-score? It's going to be like ridiculously high. It'll be like, a couple hundred standard deviations away from the mean. So what we actually need to put in here would be the natural log of that cutoff value we're interested in. So we're still converting this into a z-score. It's just that, well, to get a z-score, we have to turn a normally distributed variable into a standard normal. Y is not normally distributed, it's log normally distributed. But we know that the natural log of y is equal to x, which is a normally distributed variable. So as long as we're looking at the natural log of different values, we can find these probabilities. Once I have this z-score, I look it up in the table, find the area to the left, right? At this point, it's like, after I have the z-score, everything's the same as what we were doing before, right? Kind of the difference here was we had to first calculate the mean and the variance for that normal distribution. And then instead of using the values for y as kind of the cutoffs, we have to use the natural log of those values of y for our cutoffs. Questions on this one? So I don't know, does anyone have, what does this end up being? Did anyone calculate it or no? What's the natural log of 400 first? 5.99, we'll just use 5.99. And then minus 6.21, what's the square root of 0.00002? So you can kind of see here, right, how far away, so what's that numerator? -0.22. This is going to be a pretty high z-score. So I chose a really bad cutoff value. I probably should have chosen something that was a little closer to 500 here, but you can kind of imagine we have a pretty big z-score here. What's that end up being? So 0.04 would go. What was it? 48? So it doesn't, yeah, negative. So we're 48 standard deviations. So I chose a terrible cutoff value for this example. But probably if I chose something that was like 480, then I take the natural, maybe we end up with a more reasonable z-score. I can then look up in the table. But really after this point, it's all kind of what we're doing before. Yeah.
So do you recommend just plugging everything like that first function in the calculator? Because that's when I got the -48. But then when you just do, like when you simplified it down, I got like -55.
Oh, because the rounding error.
Yeah,
we're looking
so
like
should we
4 or 5
round
decimals.
Or should we do the initial function?
If it's, I would try to just enter it into the equation, because you're right, if you're cutting it off at the first or second decimal, you could end up with, I mean, these are really small when we're dealing with the log normal. They're really like small differences. I mean, we have a standard deviation of 0.004, right? So yeah, if you can try to do that, this calculation all at once. I was just more so one of these so we can start to think about like how far, yeah. But yeah, as you're doing the calculation, try to put everything in at the same time. These you shouldn't really have to, I mean, these won't have your rounding errors, right? When you're using these equations, because the numbers are a little bit bigger, but yeah. Any questions like that? Does the idea of kind of what we're doing, I know it's tough because I think the toughest part about this is we're starting out with the variable we see in the data is actually not normally distributed. Right? So we first need to convert it into a normal distribution. To convert the cutoff values, we simply have to take the natural log. That's pretty easy. Right? If I'm dealing with a log normal distribution and you told me, yeah, all you have to do is use the same mean and variance, and all you have to do is take the natural log of that variable when you're calculating your z-scores. That would be a little bit easier. But it's you take the natural log of those cutoff values, but the mean and the variance that you see of that original variable y, to convert that into a normally distributed variable, the equations are much more complicated, right? It's not just as easy as taking the natural log. Notice, the natural log is a component in both of those equations, but in kind of converting that log normal to a normal distribution, converting the means and the variance, it's not as easy as just taking the natural log. There's a little bit more work that needs to be done. And you could walk, you know, I'm sure there's a mathematical proof floating around out there as to why these are the equations that would convert it. You basically start out, I didn't even show you what the probability density function of a log normal looks like, but it has its own probability density function. You have the probability density function for the normally distributed variable. And it's basically a mathematical proof of showing what needs to be altered to the mean and the variance of this log normal distribution to get it to match up with a normal distribution. And this happens to be the equations that would do that. Question? Yeah.
So when would you like use like what are some examples of like using log normal distribution in like the real world? Like what do you use this for?
So, you know, so I use these examples for a reason. So the duration on your phone, and honestly, even an exponential for a car battery, it probably would be a little bit closer to log normal, would be my guess. I don't know enough about car batteries to know if that's the case. But usually it's things where, so like you think about like the battery life on a phone, it rarely ever just stops working like 20 minutes into when you use it, right? But there are those rare occasions where it ends up like outlasting how long it usually does by a couple hours, right? So you're always going to have like this longer right tail just by the nature of whatever the technology or whatever it is that you're looking at. I would say I bet another really good one. I don't sit around and track this, but if you wanted to, you could probably map it out, be like the Guinness guy and like come up with a discovery. But I would imagine light bulbs also follow the log normal distribution. Right? You rarely see them kind of end way before the mean, but sometimes you do see them kind of outlast that mean by quite a bit. So you're always going to end up with that longer right tail. More practically, I mean, it's just hard. A lot of it's like when you observe the actual variable. You know, I would have never thought like, so I showed you the one that was normally distributed. Oh, where did it go? I thought I had it up here. Oh, I didn't go for it. Most of like human performance data looks normally distributed, but then every once in a while you end up with a variable in biology or kind of a human biometric that ends up being log normally distributed. So like you can see this play out in biometrics. So you can see this play out, you know, really in anything. So it's just more of a matter of once you actually know what you're interested in, looking at what the distribution based on historical data looks like to see like what shape does this distribution take on. Here we've got something that's kind of normally distributed, but like definitely with this like real long kind of right tail, right? Like if it's a log normal, like if you cut off the left side, it looks kind of like it could be like its own normal distribution. And then if you cut off and look at the right side, it could be its own normal distribution. They just don't match up. So it's not symmetric, right? And this one kind of makes sense as well. I'm kind of censored on the left side, right? When I'm talking about this, it's like time to complete some workout, right? Well, the smallest time I can ever see is 0, right? Like I can't see someone complete this in negative seconds. But the problem is, I can definitely take way longer to do this workout, right? I could definitely do this and take way past me. So just kind of the nature of the variable sometimes leads it to kind of being one of these log normal distributions. Other questions on this? So I think I've got this. I don't want to confuse you too much, and I'm not sure I want to like dive into this too much. Because I won't ask you a question like this, but I just want to make it like information available to you that this is possible outside of this class. So we just have this log normal. That's the only one that I'll kind of be expecting that you understand. And it's also the most common, most frequent. But we could have other weird scenarios where, like, let's say it had some variable y and it was equal to the square root of x. Well, if x is the thing that's normally distributed, then I know that y squared would be normally distributed as well, right? And so then I can convert different values for y, right? And instead of using the natural log of y in my probability, like I did here, I'd be using the value of y squared, and then I could find the the mean and the variance of my x variable by the transformation that would come from taking a square root, which is much easier than the natural log. So there's other transformations you can do, right? So if you start out with a variable and it's not normally distributed, it's not log normal, it's not exponential, it's not uniform, it may be like you still might have some ways that you can convert it into a normal distribution, right? So maybe y isn't normally any of these distributions, but it's the distribution of a normally distributed variable that you've taken the square root of, right? Or done some other transformation to. Now, does that make life harder? Yeah, it makes it a lot harder, but those are possible. So I just wanted to kind of make you aware of that. I won't expect us to do anything other than this log normal, because that's one that honestly is going to be the most frequent that you can see. So I laid out the steps here. And we could really do all this in Excel as well. So you'll see this variable y in your data set. So that individual assignment, one of the questions is treat your variable as though it's log normally distributed. What's the probability of seeing values above or below certain cutoff values that you choose? Well, you see the variable y. So in your data set, you can calculate the mean and the variance. Right? So once you have kind of that mean of y and the variance of y, right? Then it's a matter of, okay, plug them into those equations that we had, right? These two guys, to find the mean and the variance of this normally distributed variable x. In fact, I wouldn't even just find the variance. It's probably better to find the standard deviation, right? Because that's what you're going to be dividing by when you calculate your C-score. Right? So you use the mean and the variance you see in your data set from that variable, plug them into these equations to get the mean and the variance of that normally distributed variable x. Once you have that, right, you'll use that mean and that standard deviation. And if you were doing it in Excel, you can use that norm.dist function. So you'll tell it that mean and that standard deviation that you had to calculate using those two formulas. Then you'll simply put in the natural log of whatever those cutoff values you're interested in for y. So for example, if I had an income variable and that was in my data set, and I said, I see that the average in the data, right, the average of the y variable I see in the data is like $50,000. Well, what's the probability I see it averaging to be less than 45,000? Well, I have the mean of that variable, which is 50,000. I could calculate the standard deviation. I would then use those two values to come up with the mean and the standard deviation for this underlying normally distributed variable x. Once I have those two, that's what, I'm putting in here to my norm.dist function. And then that $45,000 cutoff that I was interested in, instead of plugging 45,000 here, remember, I now have the mean and standard deviation of this new variable x. So I have to convert that variable 45,000 by taking the natural log, right? This is like my x value in that z value equation. And then we always make it cumulative, right? Now we're using the normal distribution just like we were before, looking for the area to the left of that value. Any other questions on this? Might be a little bit tricky in practice. So kind of once you get to that individual assignment, I'm expecting that maybe some people kind of have a little bit tougher time with that log normal. So feel free to reach out and kind of come in and work on that. But yeah, this is a pretty good roadmap, kind of this slide here for how to tackle that. No questions, comments, concerns? Fall break starting. So did this a long time ago. I think I have the data. So I'll kind of take a look at this. Relating things to the normal distribution. I think that's all I have here too. Yeah. So we'll do this real quick. Try to get you out of here a little bit quicker than. Oh, and it's not in this one. It's going to be in an old one. So let's see if I can find it. There you go. So this is a few years ago now. I think it must have been before they won the World Series. But the Cubs, so I don't know, you may not be baseball fans. It's not that big of a deal. Basically, if there's like 5 teams in a division, but there's several divisions, you could be like third best in your division, but better than everybody else in your other division, right? So like your division is stacked, like whatever. And then you can think about this as sports. You can think about, your area within a company, right? And so, the Cubs finished third in their division with, what was it? I have it in here somewhere. $97 wins, right? So they, they had an amazing year, but still didn't finish first in their division. So you can actually figure out, here, actually, I think 97 was I played around, but with 95, I think was the actual number of wins. So what I could do is I just went out and grabbed all this data and figured out on average, what's the number of wins that would get me first place based off of the historical data? What's the number of wins that would get me second place? And what's the number of wins that would get me third place? Right? Well, if these things follow even remotely close to a normal distribution, which it's not perfect, but pretty close here, right? Then all I have to do is take that variable, find the mean number of wins that gets me first place, and then find the kind of standard deviation. So that's what I did here. The number of wins that gets you first place, I would just take the average of that, I call it first wins, but it was the number of wins that got you first place. So I found the average, I found the variance, and then took the square root to give me the standard deviation. Well, and then it's just a normally distributed variable. So I said, okay, if I won 97 games and, I have the average number of wins that usually gets first, the variance on that, and this is going to give me the area to the left. So what this is saying is, if I win 97 games or less, there's a 66% chance. But really makes probably a little more sense to do 1 minus that. So if I win 97 games or more, what's the probability I end up in first place? So about a 33% chance, right? But they in fact did not that year, right? So not only did they not get first place, right? They also ended up getting third, right? So then I said, okay, well, how likely was that? Well, you can find the average number of wins that would give you third place, the variance on that, the standard deviation. So here I said, okay, if I were to win 95, actually, there it is, 97 games, and here's the kind of average number of wins that the third place team gets. Here's the standard deviation. What's the probability I end up in third place with 97 wins, right? And I could do 97 wins or greater, right? So I took this probability and subtracted, actually, I didn't do that, but I could subtract it from 1, and that probability is really, really small. Well, I then was like toying around with what's the probability if I won between 95 and 97 games? What's the probability I end up in third? So there, I'm looking for the probability of being in between two values. So I can take the higher probability, subtract the lower probability, which is what I did here. And you find that if I win 95, 96, or 97 games, right, somewhere in that range, that the probability I actually end up in third place was 0.0002. All right, so it's incredibly low. Right? But this is just like a good example where as long as you find a variable that's normally distributed, you can calculate the mean, you can calculate the standard deviation in Excel, and then just start playing around with different values. Now, this isn't a perfect example. Why? If I'm dealing with the number of wins, it is not continuous. I can't get 0.3 wins, right? So it's a little bit, but one thing that's kind of weird, just to mention it here, if I have the number of wins, how could I pretty quickly turn that into a continuous variable? It's kind of weird, but if I had the number of total games played, I could actually do something like win percent. And now when I divide these by the number of games played, I can see any decimal value there, right? It's a little bit, and it's weird. So we haven't really gotten into it yet. When we come back on Wednesday, we'll start talking about sampling and biases that exist. And we'll then start talking about the sampling of continuous variables. We'll also start to talk about when we do sampling with proportions. So kind of what I have here, it's not perfect, but I'm turning these number of wins into the proportion of wins that I got. And what actually ends up being true about those proportions is that they're normally distributed, right? So even though we started out with something that's not continuous, by turning into a proportion, we now have a variable. So if I wanted to really do this to be like theoretically 100% accurate, I should have been doing like the win percentage, but it's easier to think about wins and it kind of gets to the same point across. And I thought it was kind of a fun little example. So, yeah, I don't know. Maybe you guys can find that interesting at all. I don't know. I think it's interesting how often things like pop up that are normally distributed. And then I think I'll leave you with this because that's one of my favorite memes. But we've talked about z-scores. So always, maybe try this one out. The hypotenuse is a normal distribution with the 3 standard deviations above the mean. If you want to make it even more nerdy, tell somebody that they're a z-score of 3 and see like if they get it. If they get it, then like you found someone who's good. If not, just like walk away. Right? So, all right, I'll leave you guys with this. Try to decompress, take fall breaks, kind of get a kind of relax a little bit, and we'll pick back up on everything on Wednesday. Okay.